Hi everybody, this is Skip Elsheimer. Welcome to the AV Geeks Lunchtime Streaming Show, where we watch old 16mm films. And we're in the archive today, but we're not really in the archive today. We are at Dollywood, hopefully riding a bunch of roller coasters or thrill rides. It's been a while. I'm a big fan of roller coasters, and so I'm excited to be paying more than $100 to do it. Man, theme parks are so expensive now. Anyhow, so this is a pre-recorded show, and we got some stuff for you that's all related to gravity. So the first thing we're going to watch is something from the Prelinger archive called Simulation of Two-Gyro Gravity Gradient Attitude Control System, which is an amazing computer animated thing. Then we're going to watch a Cornet film called Gravity. Then we're going to watch Galileo's Laws of Falling Bodies, Force of Gravity, and then we're going to wind it up with, we digitized a bunch of stuff for NASA, for the Internet Archive, and so this is a episode of a show called 321 Connect, and it is about microgravity, and I've edited it down because it was 30 minutes, but I've made it short and taken out the live classroom participation aspect of it, but it's still pretty interesting, and I think John Glenn's in it, so and some really bad late 90s animation. So thanks so much for watching today. I appreciate your eyeballs and I appreciate your comments. I might try to check in. I don't know. Well, we don't know where we're going to be. We don't know if I'm going to have phone access in the mountains. But regardless, thanks for your support. You can support us by hitting the thumbs up or the like button. You can also support us with coffee by going to ko-fi.com/avgeeks or patreon.com/avgeeks. You can also go to use the super thanks button in the YouTube comments. That's another way to financially support us. But just hitting that thumbs up every once in a while, that's great for the algorithm. Yeah. Everybody have a great rest of your weekend or beginning of your weekend. And we'll be back live, provided I can drive down the mountain, on Monday. And we'll see you soon. Everybody take care. Bye.
Did you ever stop to wonder why it is that things seem to fall toward the earth? That's what Bob did one Saturday, resting after a game of touch football and watching the autumn leaves drifting down from the trees. Almost everywhere you look, you can see examples of the downward pulling force known as gravity. Gravity pulls children down the slide in the playground. Gravity pulls down on a ball all the time. Even though you can kick the ball high into the air, gravity keeps pulling and brings the ball back down. What is this thing called gravity? It even holds Bob down. And airplanes have to use power to stay in the air against gravity. Bob was wondering what would happen if there were no gravity. And that's where I came in. I know Bob. I'm an engineer at the same plant as his dad. So he asked me what I could tell him about why things seem to fall toward the earth. Well, I was on my way down to the plant, and I suggested Bob come along. We'd see what we could work out together. Gravity is so common that many people don't even stop to think about it. Our bodies and things all around us are held to the earth. Yet there is more to gravity than that, I explained to Bob. To appreciate gravity, you must understand what Sir Isaac Newton meant when he formulated the law of gravitation. As it's sometimes expressed, mutual attraction exists between all bodies. Those are big words for a big idea. But gravity's mutual attraction between bodies is something like the magnetic attraction between two magnets. Each is attracted to the other. That's what we mean when we say that the attraction is mutual. And just as in magnetism, where a larger, heavier magnet can have a greater attraction or pull, so in gravity, the heavier the bodies, the greater the gravitational pull. Bob could understand mutual attraction between magnets, but was there any mutual attraction between him and that desk, for instance? Well, that attraction is very small, but it does exist. We engineers know that it does because we've measured the attraction with delicate instruments. You measure gravity's attraction every time you weigh something. Now, the Earth has a mass billions of times as much as Bob. So it attracts him with considerable force. We measure that force to be 120 pounds. And because my mass is greater than Bob's, 164 pounds is the measure of the mutual attraction between me and the Earth. How does this attraction of gravity affect our solar system? Let's look at it in miniature. Suppose the Earth were the size of a grapefruit. At the same scale, the moon would be about the size of a golf ball. And they would be about 10 feet apart. Nearly a mile away, there would be another round object, say that water tank, about 36 feet in diameter, representing the sun. Mutual attraction keeps these bodies in their places in the solar system. Why don't they come crashing into each other? Well, it might happen if it were not for the fact that all heavenly bodies are traveling through space at tremendous speeds. But the moon, for instance, doesn't go flying off in a straight line because of gravity's mutual attraction between the Earth and the moon, which we can represent by a 10-foot string. Centrifugal force tends to keep the moon going in a straight line, but the force of gravity, represented by the string, pulls it into a circular path or orbit. For For exactly the same reasons, the Earth moves around the Sun in its own much larger orbit, pulling the Moon along with it. Bob was worried about something. If gravity's attraction is dependent on mass, then does the little Moon have less attraction than the Sun? I was pleased. Bob was really trying to figure this thing out. He was almost understanding Newton's law of gravitation. Gravity does depend directly on the masses involved. But it's inversely proportional to the distance, to the square of the distance. If two objects are moved twice as far apart, the pull of gravity is 1/4. So there's our Sun, almost 400 times farther from the Earth than the Moon. It all made sense, Bob said. The greater the distance, the less the attraction of gravity. When you understand how the attraction of gravity falls off as the square of the distance, you appreciate how spaceships may travel by rocket to the Moon or to other planets. I've been playing around figuring space travel, and the pull of gravity works like this, I told Bob. Say you're here at the surface of the Earth, 4,000 miles from its center. That's the radius of the Earth, 4,000 miles. You weigh 120 pounds. That's normal here at the surface. But you take off in a spaceship. Now you're out 4,000 miles from the surface, really 8,000 miles from the center of the Earth. Being twice as far from Earth's center cuts the pull of Earth's gravity to 1/4. He'd weigh only 30 pounds. The attraction of gravity is inversely proportional to the square of the distance. And up here you must use rocket force in reverse to overcome the Moon's gravity and prevent a crash. I had some movies there of the first experimental rocket flights. The force of the rocket motor overcomes the force of gravity and slowly lifts the ship. But these early rockets went only about 100 miles up before they ran out of energy, and gravity pulled them back to Earth. So Bob had a better understanding of gravity, the mutual attraction between bodies. And then he said he'd always thought of down as this way. But actually, to a person at this point on the Earth, this way is down. And to a person here, this way is down. This person is not upside down. As long as you're on or near the Earth, down is toward the center of the Earth. This gravity is attracting everything, solid things, liquids, and even gases, the air around us. Every time you lift something, you're working against the pull of gravity. But we put gravity to work, too. We hoist coal into trucks and let gravity pull it down into our basement. And in the furnace, the coal heats the water for our radiators. When the air around is warmed, it expands, becoming lighter than the cold air around it. So gravity pulls the heavier cold air down, forcing the warm air to circulate and heat the entire room. And so it was that the curiosity about leaves falling down from trees led to an understanding of gravity's mutual attraction between bodies and its importance to our solar system and to so many things on Earth. For example, Bob can figure out the part that the force of gravity plays in drinking through a straw. Can you?
Gravitation draws all objects toward the Earth's center. As long as the Earth has existed, objects on the Earth have been acted upon by gravity. But laws that govern freely falling bodies, suspended bodies like this pendulum, or other bodies in motion, were not discovered until the latter part of the 17th century. Galileo, often called the father of modern science, is given credit for helping to develop these laws of motion. According to legend, the Leaning Tower of Pisa was used by Galileo. Supposedly, he dropped objects from the top of the tower and observed how fast they fell. Regardless of whether Galileo made these experiments, we do know that he did research in the physical sciences. Here in this modern physical science laboratory, we will recreate some of his experiments. For example, he dropped objects of different weights and sizes and compared their rates of fall. We will make the same kind of comparison by using slow motion photography. Based on such observations, Galileo concluded that all objects fall at the same rate of speed or acceleration, regardless of size or weight. Objects that weigh very little, such as this feather, seem to be exceptions. But Galileo believed that any differences in acceleration were the result of air resistance. Today, we can prove that Galileo was right by using a glass tube from which the air has been removed. In the vacuum that results, the feather and a coin fall with identical acceleration. Here is the action repeated in slow motion. Another problem challenged Galileo. He wanted to describe the speed of a falling body at any instant. Freely falling bodies move so fast they are difficult to observe, so Galileo devised an inclined plane, much like this one, to reduce or dilute the speed of fall. Galileo used a water clock to time his experiments. Here, a modern electric timer is used to click off the seconds as the object falls. And this device releases the object, such as the steel ball, and simultaneously starts the timer. The distance the ball rolls in each succeeding second varies depending upon the elevation of the plane. Now we will see the action in slow motion. After 1 second, the ball has traveled 10 centimeters. In 2 seconds, 40 centimeters. In 3 seconds, 90 centimeters. In 4 seconds, 160 centimeters, and so on. Here are the experimental results. Using similar facts, Galileo noticed that a relationship existed between the distance traveled and the time squared. Using our experiment as an example, at the end of 1 second, the ball has moved 10 centimeters. At the end of 2 seconds, it has rolled 10 centimeters times 4, or 10 times 2 seconds squared. At the end of 3 seconds, the distance is 10 times 3 seconds squared. And at the end of 4 seconds, 10 times 4 seconds squared. As a formula, s, the distance, equals 10 times the number of seconds squared. Expressed in terms of acceleration, s equals 1/2 the acceleration times the seconds squared. This formula applies to all objects in motion, such as the ball moving down the inclined plane. For the special case where an object is falling freely instead of rolling, the formula s equals 1/2 at squared becomes s equals 1/2 gt squared, where g is the acceleration due to the full force of gravity. Although the Tower of Pisa experiment, so often associated with Galileo, may never have actually taken place, there is no doubt that Galileo deserves an honored place in the history of physical science. He was a pioneer in experimental work, and he developed formulae to represent some of the basic laws of motion.
Governs its motion. What goes up must come down. With an old saying, man has unconsciously tried to sum up a basic force in his universe. This force is one of the most familiar things in the world, yet nothing has puzzled scientists more. Despite all their study, it is still a mystery. It is known as gravitation. Man has long known how to use gravitation. He has also learned recently to overcome it. But he still asks the same kind of questions that he asked thousands of years ago. What is gravitation? Why does it act the way it does? Man's wondering about such things has inspired many theories about the world around him. Ancient civilizations looked for order and harmony throughout the cosmos. According to the Egyptians, the goddess of the heavens arched her body like a canopy over the earth, holding up the stars, the planets, and the sun, and letting them glide over her back once each day. In one Greek cosmos, a large earth was surrounded by concentric spheres, which carried the moon, the sun, the other planets, and the stars around it every 24 hours. Within this universe, 4 elements fell naturally in place. Earth, the heaviest at the bottom. Water, not so heavy on top of it. Then air, much lighter. And then fire, lightest of all, high above everything. Weight was important in this cosmos. The Greeks were trying to deal with gravitation, although they did not know that such a thing existed. Such a cosmos, with the Earth at its center, appealed to an age whose philosophers believed man to be the center of all things. This neat and logical universe won Aristotle's approval, which helped it remain in favor for nearly 2,000 years. But in the 16th century, the Aristotelian cosmos was successfully challenged by the Polish astronomer Copernicus, who adopted another concept. Here the sun was at the center of things, and the Earth merely one of several planets orbiting around it. This universe was refined nearly a century later by the German astronomer Kepler, who combined the Copernican view with new observations and worked out laws describing rather simply the motions of the planets. Kepler found that each planet follows an elliptical path and travels faster when it is nearer the sun. He also found a simple relationship between the period of a planet's revolution and its distance from the sun. The period squared is proportional to the distance cubed. With this formula, Kepler, without knowing it, provided a clue to the sun's gravitational field. Meanwhile, the Italian Galileo was studying the motions of much nearer objects. One morning in church, his attention was caught by a swinging lamp. Although each swing was smaller than the one before it, the time of each swing was the same. Galileo wondered why. In trying to solve problems like this, he became one of the first to perform practical experiments with motions and forces, and to understand what those experiments implied. Galileo showed that the fall of all bodies toward Earth is independent of any other motion, such as horizontal movement. He also demonstrated that no matter what their size and weight, all falling bodies gain speed at the same rate. He concluded that force is necessary only to change the speed or direction of motion. Galileo's findings led ultimately to an explanation of the motions of all massive objects on Earth. It remained for the 17th century English genius, Sir Isaac Newton, to connect Galileo's experiments, Kepler's equations, and the universe of Copernicus. Newton's view of the physical world gives us the basis for solving practically all our problems in mechanics. For example, his own drawing showed that if a projectile were hurled at greater and greater speeds, it would become a satellite. Newton was the first to state that all motion, whether of projectiles, pendulums, or planets, is subject to the same kind of force acting under different circumstances. In this monumental work, he set forth a universal principle based on his studies of motion. Newton stated that each body of matter in the universe is attracted to every other body. The greater the mass of a body, the greater its attraction. The greater the distance between bodies, the less the attraction. Newton's formula states that the attraction between bodies is proportional to the product of their masses divided by the square of the distance between them. To this fundamental attraction, Newton gave the name gravitation. He also stated that every massive body is held together by self-gravity, the attraction between each of its own particles of matter. Thus, the history of any star, our sun, for example, came to be understood as a vast struggle between equal forces. The fiery energy that tends to blow the mass apart, and the gravitation that holds it together. The balanced, ordered universe described by Newton reigned supreme for more than 2 centuries. And within this classical framework, man began to make sense of more complex motions controlled by gravitation. He learned how to make accurate predictions about the motions of astronomical bodies. These predictions, in turn, led to important discoveries. For example, from various observations, astronomers calculated the orbit of the newly discovered planet Uranus, taking into account the location and gravitational influence of other known planets. But very soon, Uranus was seen to wander slightly from its expected path. Studying the direction, amount, and time of the planet's deviation, astronomers concluded that another body in space must be attracting Uranus. And they were right. In 1846, the body was discovered as predicted, identified as a planet, and given the name Neptune. Since then, Newton's law has helped astronomers understand the structure of galaxies and other great star systems, how they are held together, and how the material in them is distributed. Moreover, with the development of precise instruments and methods of measuring gravity, man has become able to map the distribution of mass on his own planet. In 1798, the English scientist Henry Cavendish, using equipment built like this model, found a way to measure the gravitational attraction between known masses a known distance apart. The amount of attraction exerted by the larger masses on the smaller ones at the end of the torsion balance can be measured by the degree of twist in the suspension fiber. Thus, once man learned that a specific mass exerts a specific amount of attraction, he could calculate the amount of mass in any object by the amount of its attraction. In the last century, man has measured gravitational attraction all over the Earth, and he has used the relation between mass and attraction to interpret his measurements. However, on Earth, these measurements are greatly affected by the fact that our planet is rotating. First of all, the Earth's spin carries an object along much faster at the equator than near the poles. Therefore, the pull of gravity is counteracted more at the equator, and the object there weighs less than an identical object near one of the poles. Furthermore, rotation causes the equatorial zone to bulge and the polar regions to flatten. This brings objects near the poles closer to the Earth's center and places objects at the equator farther away. The difference in weight between the two identical objects is thus even greater. For example, if on a spring scale at the Panama Canal you weigh 193 pounds, in Greenland, even without the extra weight of the boots, you will weigh a pound more. And the bob of a clock pendulum, adjusted to keep perfect time at the poles, will weigh less at the equator and swing more slowly there. Thus, the clock will lose about 10 seconds an hour, about a day a year. Since the period of a pendulum swing depends on gravity, the pendulum is a good instrument for measuring gravitational acceleration. This is usually done by measuring the total elapsed time of a large number of swings. In this way, the absolute value of gravity has been found at stations throughout the world, such as Teddington, England. The figure shown here is derived from the length of a pendulum and the average time taken by its swings. To get such a reliable measurement, the Earth's magnetic field must be nullified. The pendulum must swing in a vacuum chamber, free of air resistance, moisture, and temperature changes that would affect its motion. At a number of stations throughout the world, including the National Bureau of Standards in Washington, scientists are measuring the acceleration of gravity directly. A rod is designed to fall freely in a vacuum inside a tube. Spaced holes in the rod act like a camera shutter, allowing light to pass to a recording device when the apparatus is dropped. The time between flashes is measured to the nearest 10 millionth of a second, providing a direct measure of acceleration. Thus, modern technology refines Galileo's original experiment. Using the pendulum stations as reference points, scientists measure gravitational variations all over the world. Moreover, in the last few decades, they have been able to take measurements in the vast oceans covering nearly 3/4 of our planet. Measuring gravity at sea is more difficult than on land. The acceleration of gravity must be clearly differentiated from the motions of the vessel. This problem was solved in the 1920s by the development of an instrument which used the classical pendulum in a new way. Identical pendulums swing in opposite directions on a supporting frame. The frame is hung on gimbals to reduce the influence of the vessel's roll. The pendulums are swung for about half an hour, and the vessel's accelerations are averaged out. The average acceleration acting on the pendulums is the local value of gravity. Under the best conditions, error in measuring can be reduced to 3 or 4 parts in a million. Gravity can now be measured more quickly and economically from surface ships, due to recent advances in instrumentation. This gravity meter is hung on gimbals, which keep it relatively unaffected by surface rolling and pitching. Other gravity meters are used to make measurements from aircraft and on land. Many of them are portable. All operate on the same basic principle. Gravitation exerts a pull on a weighted arm suspended on a spring. The arm, shown here on a different mount, is connected to a pointer. A measurement is made by adjusting the pointer to 0. How far the knob has to be turned at each location indicates the difference in gravitational pull between that location and the previous one. The spring-balanced gravity meter is so sensitive that it will measure the difference in pull between two adjacent positions, even if one of them is only a few feet closer to the center of the Earth. During the International Geophysical Year, the measurement of gravity was increasingly standardized and extended all over the Earth. A worldwide network of gravity bases was developed. In collecting gravity measurements around the world, scientists often stop only long enough to take the local reading before proceeding to the next point. Sometimes the gravity meter is sent by itself to be met and used by someone stationed at each place. Along with gravity, whether measured on land, at sea, or from aircraft, altitude must be noted so that the gravity reading may later be adjusted to the sea level standard. At gravity research centers such as the University of Wisconsin, data are gathered from all parts of the world. The traverses and findings of the field parties are plotted and compared. Traverses are sometimes made on foot and readings taken very close together. In this way, a detailed gravity portrait of large areas is built up. Taken from notes made in the field, the exact position of each station is used to correct the actual reading for the differences in the Earth's gravity field at different latitudes. Corrections are also made for the tidal pull of the moon, for temperature, and for possible drift of the gravity meter. On this geological map showing rock distribution, corrected gravity readings are plotted in the form of contour lines, indicating local excesses or deficiencies in gravitational pull. The gravitational pattern, when compared with the geological pattern, provides geodesists and seismologists with important clues to the structure of the Earth's crust. Although gravity measurements vary from place to place, the large visible masses do not cause as great a variation as might be expected. This can be explained by the way the Earth's hard crust floats on the plastic mantle underneath. In a normal region where the land is not very high, the crust is generally about 20 miles thick, and only a small fraction of it floats above sea level. In a mountainous region, the crust sinks deeper into the mantle to support the extra weight of the mountains. This deep projection is known as a mountain root. On the other hand, in the oceans, only a thin crust is needed to support the water, which is less than half as heavy as rock. In this ideal picture, all these floating sections have about the same weight and mass. Therefore, they would exert the same pull on a gravity meter. This equalization of masses is called isostasy. Actually, the Earth's crust departs from this ideal picture. Different sections have different weights and masses. For example, a mountain root may be missing and replaced by denser mantle. Such a section will have a greater weight and mass. Gravity meters will detect sections like this. Here, buoyancy alone does not hold up the mountain. The crust on both sides is strong enough to do much of the job. On a larger scale, gravity readings adjusted to measurements made at pendulum stations indicate slight lumps and hollows in the Earth's sea level figure, which we call the geoid. Thus, a clearer picture of our planet's irregular shape is emerging. Most of the gravitational effects that man can now measure with his gravity meters originate in the Earth. But beyond these effects, there is a dramatic phenomenon caused by our nearest neighbor in space, the Moon, and to a lesser extent, by the Sun. This phenomenon is the great cycle of tides. One side of the Earth is about 3% nearer the Moon than the other side. Thus, according to Newton's law, masses on the near side are attracted by the Moon about 6% more strongly than masses on the far side. The waters on the near side are pulled out and gathered by the Moon to form a high tide. And since the solid Earth as a whole is nearer the Moon than the waters on the far side, the Moon draws the Earth away from those waters, thus leaving another high tide. The Earth rotates under the tidal humps, and the continents and sea bottoms resist the flow of high water. This friction carries the tidal humps out of line with the Moon. Depending on the Sun's position relative to the Moon, tides caused by the Sun pile up on the high tides caused by the Moon, or fill in the low tides. The gravitational pull of Moon and Sun also affects the Earth's crust and mantle. While the solid Earth is much less deformable than the oceans, sensitive instruments have measured tides in the Earth up to 8 inches at the equator. This rise and fall provides information about the rigidity and strength of the crust. During the International Geophysical Year, measurements like these also helped us understand more about small shifts in the Earth's crust caused by the pull of the Moon and Sun. Ever since man started launching satellites and studying their orbits, which are governed by the gravitational field around Earth, he has been learning new details about his planet's shape as a whole. Studies of orbits have suggested that the gravitational field around our planet fits a slightly raised Arctic and a slightly flattened Antarctic. Man's conception of the way gravitation behaves has been formed almost entirely within the framework of the universe conceived 3 centuries ago by Sir Isaac Newton. Today, as man gets ready to venture far beyond planet Earth, Newton's laws still apply to most of his physical existence, even the motions that he experiences in the strange state of zero gravity. In this free fall, everything happens the way it does in empty space, far removed from massive bodies and their gravitation. On the other hand, to a man in a centrifuge, everything happens the way it would near a massive body with tremendous gravitation. Here, if a man's weight is increased 10 times, we say he is subjected to 10 Gs. Is this force essentially the same as gravity? And is a free fall really the same as the absence of gravity? Classical physics said no. Albert Einstein was the first to say yes. This answer has led 20th century physicists through a series of logical steps to a new concept of the universe. Gravitation is no longer thought of as a force exerted through empty space by one mass on another. Instead, it is regarded as the way a freely moving body takes the shortest path through space-time. A mass curves the space around it, and measurements obey a curved line geometry. The greater the mass, the more extreme a gravitational field it creates. The new concept of gravitation still allows us to drop a ball, build a bridge, and fly a plane as we have done. But where we can study objects moving at speeds near that of light, in the laboratory, or out in boundless space, we find that time stretches, distances shrink, and bodies become heavier. It is difficult to grasp this universe. We can only keep on observing, measuring, and studying gravitation, along with other cosmic forces. Today's scientists ask many questions. Does gravitation weaken with time, or possibly grow stronger? Is gravitation different in different parts of the universe? If tomorrow's scientists can answer questions like these, man will have a far more profound understanding of the way this force brings order on planet Earth and throughout the universe.
Did you know that some of the sensations you experience in a roller coaster 200 feet above the ground are similar to sensations experienced by astronauts some 200 miles above the Earth?
On today's Connect, we're going to look at the world of microgravity. It's something we feel every day, and not just in theme parks. Hi, I'm Van Hughes.
And I'm Shelley Canright, and we're here at Busch Gardens, Williamsburg in Virginia. Welcome to Connect, the show that connects you to NASA into the world of mathematics and science.
On today's show, we'll look at how microgravity works here on Earth and in space.
And we'll look at some of the benefits we get back here on Earth from experiments conducted in a microgravity environment. Now, to help us explore the world of gravity and microgravity, we've enlisted the help of some very special friends.
First, we'll talk with Dr. David Wright, creator of the Busch Gardens Physics Fair in Williamsburg. He'll explain how roller coasters simulate microgravity here on Earth. Then Shelley will talk with an expert who felt the effects of microgravity in space. America's first astronaut to circle the Earth, Senator John Glenn.
That's right. And then shortly, we're going to take you to the Connect studio back at NASA Langley. We'll talk to two NASA scientists who are studying the effects of microgravity on fluids and protein crystals.
And later, you'll be able to phone in questions or email them live to our studio and to our microgravity scientists, Nancy Hall from NASA Lewis Research Center and Felicia Ewing from Marshall Space Flight Center.
And then finally, we'll also see a class of students from the Williamsburg, James City County, and York County school districts in Virginia who have done an experiment related to our topic. We'll share their data with you and then get you involved in the analysis of the data. It's a great show we've got lined up for you.
Well, Shelley, I'm set to find out how sensations on a roller coaster are not too unlike those that astronauts feel when they're in space. So I guess we'll see you at the Connect studio?
Hey, sounds good, but right now, I'm gonna ride one of those coasters. See you there.
All right, see you. Well, I wonder where Dr. Wright is. He told me to meet him here in his lab.
Man, welcome to Busch Gardens, Williamsburg, the Enchanted Lab.
Hi, Dr. Wright. This isn't where roller coasters are created, is it?
No, Van. Scientists and engineers do that. They spend lots of time using math and science to design rides like Alpengeist, the Big Bad Wolf, and one of my favorites, the Loch Ness Monster.
Oh, the Loch Ness Monster. That's the ride Shelley just went on. It's really great. What makes a roller coaster so much fun? It doesn't take magic, does it?
Well, Van, it has a lot to do with velocities, banking angles, and gravitational forces.
Gravitational forces?
Professor, explain the process of gravitational forces to Van.
To understand gravitational forces, you have to understand the problems of gravity. I'll begin with the story of a fellow named Galileo. Gravity is the attraction that holds us to the ground. Here on Earth, the gravitational force we feel, we measure 1g. In 1630, Italian scientist Galileo went to the Leaning Tower of Pisa. In his hand, he had a 1-pound ball and a 10-pound ball. He dropped these balls at the same time from a great height and learned, to the amazement of the people below, the balls fell at the same rate. How can this be? One weighed 1 pound and the other weighed 10 pounds, yet both fell at the same rate. Galileo showed that the pull on the objects was the same. This pull we call gravity. Gravity! Now, if a man and an apple were to drop from the same tower, the apple would appear to float before his eyes because both are falling at the same rate. This is called free fall. It simulates the effects of weightlessness. You've seen footage of astronauts in the space shuttle, haven't you? Well, they're not floating. What actually happens is that the space shuttle, the astronauts, and everything in it is in a continuous state of free fall. Because NASA shoots a rocket with astronauts and experiments to heights greater than the Leaning Tower of Pisa, Galileo's experiment is replicated for longer durations. At this point, the spacecraft orbits the Earth. Unfortunately for this man from the tower, he didn't get on a rocket ship in time.
Thanks, Professor.
You're welcome.
Let me explain microgravity, Van. Have a seat.
Okay.
Microgravity means small levels of gravity or low gravity. We can simulate in a number of everyday experiences. You feel microgravity on a playground swing when it gets to the top. You feel it when an elevator drops. And you feel it on a dropping roller coaster. And you get that feeling that your stomach is rising up into your throat.
I think I'm feeling it right now.
Oh, I left the microgravity chair on. Van, come on down. Van, the point is, you don't need magic to experience the effects of microgravity. You feel it all around you. You can study it in lab situations.
That's right. NASA uses several unique laboratories to create microgravity conditions here on Earth. Some NASA researchers use free fall here on Earth by placing experiments into containers and dropping the container down a chute to a cushioned landing. These are called drop towers. Another laboratory is a flying one. By flying aircraft in a careful series of roller coaster-like arcs, brief periods of microgravity can be produced. Usually, about a quarter minute to a whole minute can be sustained. One final tool used by NASA are sounding rockets, which arc high above the Earth before parachuting down to be recovered. But all of these laboratories share a common problem. After a few seconds or minutes of low gravity, Earth gets in the way and free fall stops. Right, Professor?
Right. And where is the place where free fall is constant?
Space.
Right.
Well, that's where we're going next. And one person who has been in space and is preparing to go up again is America's first astronaut to circle the Earth, Senator John Glenn. He'll tell us some of the benefits microgravity research has on space and for us on Earth. Just a few days ago, Shelley talked with Senator Glenn. Let's see what they have to say.
Today, I have the distinct pleasure to talk with the first American to orbit Earth and to experience firsthand microgravity in space. Joining the Connect program is none other than test pilot, astronaut, and American hero, Senator John Glenn.
Thank you. Glad to be with you. Thank you.
Glad to have you. We appreciate your time, that you can help our viewers learn a little bit more about microgravity research.
Good.
Could you share with us maybe some of the areas of research that are going on?
Well, there are lots of things go on. You know, they're doing research with how a match burns or what happens with combustion. In other words, a burning process. Does the fire just collect in a ball around whatever is burning instead of going up like a candle flame? That's different in space, and so you learn a lot about combustion from that. We do research with protein crystals growth. Protein crystals, which are tiny little crystals that can be used for new kinds of research on medicines. These crystals can grow larger and more pure in space than they do here on Earth. Now, you can't do that in 25 or 30 seconds in an airplane, so you have to be up there in space and run research in that area. They're doing research in areas like tissue culture. Now, tissue culture means you're trying to grow tissue, like body tissue. And if you do that in a laboratory, like experimenting with cancer cells, for instance, they'll grow flat as a tissue growth occurs in the bottom of a glass dish in a laboratory. But in space, you can grow them in the natural shape that they would have inside the human body, and so have a better chance to learn how to treat them. So those are things we'll all be looking into, and you can't do those things in an airplane short term. You have to be up there in a spacecraft for longer term.
Is there a message you'd like to leave with this younger generation?
Oh, indeed there is. You know, I think I hope they're very curious, and I hope they keep that same kind of curiosity in school and learn more, because that's what will enable them then to take the experiences that I and others have had and do some of these things themselves. I hope every young person that's watching this program has a chance to go up someday and do some of this kind of research themselves.
Well, you certainly are a great example to them and a role model. And Senator, I thank you for your time, and I'm sure that I will speak on behalf of all our viewers in wishing you the very best on your mission in October and the future that you're going to bring to biomedical research.
Thank you.
Godspeed, Senator.
We're really looking forward to it. Thank you much.
Thanks, Shelley. We want to acknowledge Busch Gardens Williamsburg and Dr. David Wright for letting us experience microgravity firsthand. Thanks, Dr. Wright.
My pleasure. And to the audience, the next time you go on a roller coaster, try to find the number of times you'll experience microgravity. And remember, math and science make it happen, not magic!
Connect with us next time when we connect you to math